Today's topic is AC power and power triangle. And if you're a surface warfare officer or submariner, then you'll want to pay close attention to this topic. You'll see it again at nuke power school for sure, and you just might have this topic come up during your nuke interview and on your SWO board. All right, so by now we know that the same physical laws that govern voltages and currents in DC circuits apply to AC circuits as well. Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law, law of conservation of energy. Now, we know that in DC circuits, that power is equal to volts times current, which is also equal to I squared R, which is equal to V squared over R, and the units are in watts. In AC circuits, power is still equal to volts times current, but its expression is a little bit more involved. And that's because the voltages and currents are constantly changing, but periodic. And we have to consider the energy storage elements, that is, inductors and capacitors, as they store energy from and release energy to the circuit. Now, there is a rigorous mathematical model we use to calculate power in the phasor domain, and it looks similar to its cousin in DC circuits. We say that S, with an arrow on it, indicating a vector, is what we call complex power. And that is equal to the phasor voltage, V with an arrow on it, times the complex conjugate of the current phasor. It's also equal to the magnitude of the current phasor squared times the impedance, shown here, which is also equal to the voltage phasor magnitude squared divided by the complex conjugate of the impedance. Now, suppose, let's just talk about the operator complex conjugate for a moment. Suppose my current right here, I have an example of 1.5 amps with an angle of 90 degrees. Well, by definition then, the complex conjugate of that current is going to be equal to the magnitude, that doesn't change, minus or the opposite of the angle that's shown here. And this is again in the phasor form of it. So it's a minus 90 degrees. And same thing with the impedance. If I have a impedance in the rectangular coordinates is equal to the resistance or the real part of resistance plus the reactive part is the imaginary part. And that's representing the ohms of the value of ohms for the inductor or the capacitor. So for example, if I have 20 plus J30 ohms, then the complex conjugate of that value is 20 minus J30 ohms. Okay. The result of that complex multiplication we call the complex power, measured in what we call voltamps, and that's different than watts, but we want to make it sound similar to multiplying volts times current, so we call it voltamps. In rectangular coordinate system, we have the real part, which is real power, as you can imagine. Here's P, and the real or average power we call watts. And that's the same watts, same real power as we discussed with the DC circuits. Now we introduce a new concept, and that is that we have a scalar value we call Q, and that's called reactive power, and the units are in voltamp reactive, or VARs. And this scalar value Q is the component of my complex power that represents my inductors and capacitors, power that's shifting around between releasing and storing, and so forth. And that's Q. In the polar coordinate system, the magnitude of my complex power vector is called apparent power. Now remember that these vertical lines around my vector tells me that I want to find the magnitude of that, which is the square root of the sum of the squares of a right triangle, basically. And that is, again, a scalar value, and its units are also in voltamps. Also in polar coordinates, my complex power has an angle associated with it. And I call that angle, or we call that angle, power factor angle, which will become more apparent later on. And this theta VI actually has a reference to the phasor, or the phase shift of the voltage and the phase shift of the current, which is equal to theta V minus theta I, where V is the voltage phase and I is the current phase, or theta V and theta I. Okay, so that's the definition of what a complex power is in rectangular coordinates, in polar coordinates, and this is where I'll reiterate again the importance of knowing how to convert between rectangular and polar back to rectangular when you find and compute what complex power is. Because going back to the equation, I see that I'm just multiplying two complex numbers together, and I'll get a complex number as a result. And that complex number is complex power, and I need to be able to see in both polar and rectangular coordinates what those values are in my definitions of all those values. Okay. Now, we also talk about complex power in the form of what we call a power triangle. Now, the power triangle is just showing us complex power in a graphical method. Okay. So if I were to look at this as my origin, and my x-axis is the real axis shown here, and the y-axis is my imaginary axis, then all I'm doing is plotting a single vector, S. But now I'm going to look at that graphically as a triangle, and I'm going to define that triangle either as coordinates in a rectangular system, which is P on the real axis and Q on the y-axis, or the imaginary axis, and the hypotenuse is the magnitude of that complex vector. We call that apparent power. So I have here shown P, which is real power measured in watts, Q, reactive power measured in vars, and apparent power is the hypotenuse, and that's measured in voltamps. Now notice that Q can be positive or negative. So I might also have a triangle that goes down, and my angle would be negative in this case. Notice that power is always going to be real, so it's always going to be positive. So it's going to be on the real axis and it's going to be in the positive side. But again, Q could be either positive or negative. One more thing to note is that if you have a triangle here and you're given two of the four characteristics of that triangle, then I can find the other two. So if I know that I have power, and that's given to me in a problem, and the power factor angle, then I can find S and Q by trigonometric identities. Likewise, if they were given to me Q and S, then I could find P and the power factor angle and so forth. Any two, I could find the other two, and it's just a trigonometric relationship with a right triangle, and I can find what those values are. All right, now that we've discussed what the power is, or complex power is, we've defined what the definitions are, we've talked about a power factor, we've talked about power triangle. Now let's talk about AC power as we see it as an instantaneous power. Okay. Now, what we mean by that is that suppose in my diagram here, my graph, that I have a current shown here and a voltage shown here, and those currents and voltages are in phase. And if at any instant in time I multiply current and voltage, any instant in time I multiply current and voltage, I'll see that I'll have a positive value where they're both positive, and also a positive value for when they're both negative, because I'm multiplying the two together. What this yields is a power that looks almost like it's pulsating, up and down like this. Okay, twice in a single period of my frequency, or the period of that wave signal. All right, that sinusoid. So what this means is that I'm going to have my voltage times current, shown here, if I multiply that together, I'll see that I'll have this expression shown here. Vm, Im, which are the peak values of the voltage and current, divided by 2, times 1 minus cosine of 2 omega t. Now, what we can see here is that if I find the average power, we can just look at this on the graph. The average power is going to be positive, and that value is shown here. That's Vm times Im over 2. Now, what we say is that that is the average power shown here, and average power is equal to the voltage times current, the peak values, divided by 2. Now, another clever way of doing that is to say that if we define everything in RMS, remember Vm divided by the square root of 2 times Im times the square root, or divided by the square root of 2, then I don't have to think about the average power as taking the peak voltages divided by 2 because I've already done it in that expression as I define them as RMS values. And so power, real power, for an AC circuit is simply equal to the RMS value of the voltage and the RMS value of the current. Okay. Now, let's talk more about reactive power in an inductor and then in a capacitor. If I have here a simple circuit shown with current flowing through as I, and a single purely inductive impedance, and I'll call that ZL. If you recall that a purely inductive reactance or a purely inductive impedance will show I have zero resistance, so zero real part, and the reactance is going to be positive, and we'll call that XL. So in the polar coordinate system, it's an angle of 90 degrees. Now, let's do the same illustration with my graph shown to the right here. Okay. If I want to find the instantaneous power of a current times the voltage across, my current would equal Im sine omega t, and the voltage here is Vm sine omega t plus 90. What does that mean? Well, again, if we recall that in an inductive circuit, we have a phase shift of 90 degrees. Again, why is that? Because if I use the mnemonic ELI or ELI, that we say that voltage leads the current in an inductive circuit. Okay, so here we have the voltage V of t that leads my current, okay, by 90 degrees. This is 90 degrees right there. And of course, to the left, it's a positive value, and that's why I have a plus 90 here. So the value, when I multiply those two, notice in the time domain what I do. When I multiply these two values here, I get a positive value for all of this region right here. But then there's a point at which the current or the voltage is going to be negative and the current is going to be positive, yielding a negative value. And then I have a positive value and a negative value. So what we're seeing here is that the instantaneous power is also a sinusoid, and the value or the answer is shown right here. Now, if I just look at that sinusoid that I just drew in over superimposed over the top of that time domain signal there, or signals, I can see that the average power is 0. And the way I look at that is I see that I have energy stored and energy released. Energy stored and energy released. And energy stored and energy released. In steady state, when I have a periodic current that doesn't change its period, it just continues on, the average is 0. So what that means is that the average power, real power, is equal to 0 for a pure inductor. It's also which is reactive power only, another way of saying that. And I'll bet that when we talk about capacitive loads, it's going to turn out to be the same thing. So shown here is a current flowing through, and I have a purely capacitive impedance we'll call ZC. And in this case, ZC in the rectangular coordinates, notice here that it has 0 real part, or the resistor, and there's a reactive part that's negative. So in the polar coordinate system, it's x of c minus the angle of minus 90. So the voltage here is going to lag the current. Okay, so here, notice I have a minus 90, and why is that? Well, that's because ICE. That is to say the current leads the voltage in a capacitive circuit by 90 degrees. So in that case, the current leads the voltage. Another way of saying that is the voltage lags the current. So here's my current that's lagged. All right, so this is my current here, and my voltage shown here is going to be lagging by 90 degrees, and that's a minus 90. Okay, now we've talked about that with the voltage and the current. The instantaneous power, again, look at and notice that if I were to take any one instant with voltage and current, I can see that there are times during that cycle where the total power is going to be negative. And then there will be times when the total power is positive and negative and positive and negative. Just like with an inductive circuit, what I'm going to see is that the average power, real power, is 0 in a purely capacitive impedance as well. Okay, so all that being said, let's move on and see that we talk about apparent power here, and apparent power is shown up again as the magnitude of the volt and the current, or the magnitude of the complex power, which is equal to the magnitude of the voltage times the magnitude of the current. Okay. Now let's put it all together. There's my power triangle. And I would like to note here that the top triangle, shown here, has the same angle as the total impedance. Okay, so the note here is that the impedance angle and the power factor angle are the same value. Okay, now we talked through what S, P, and Q are. S, another way of saying S is that we have the magnitude of the complex power, and I like to look at it in that way. But notice that sometimes it's written as just a script S without the arrow. That indicates that it's a scalar, and I like to use this method to show that it is a complex power magnitude, which is again the same thing. But remember that it's not the same thing as just straight up the S with the arrow on top, which is a vector, because I want to include the phase angle along with that. So that's the vector, and just making sure that you're understanding the difference between those two. Okay, total power in AC circuits. What we say here is that elements are connected, it doesn't matter the orientation of those elements in my circuit for total power, for computing total power. What does that mean? Well, showing off to the left, off to the right here, I have 4 elements in my circuit, and inside that box shows a power, and a real power and a reactive power, P1 and Q1, P2, Q2. So all of these are vectors of complex power, S1, S2, S3, S4. What this is saying is that the total power shown here, the total complex power, is equal to the sum of all those element powers that are in my circuit. And it doesn't matter if they're in series or parallel or some kind of network of elements, doesn't matter. Other thing to note is that ST, the total complex power, is also equal to the sum of its real and reactive parts. So that equals P1 plus P2 plus P3 plus P4 plus J, this is the reactive part, Q1 plus Q2 plus Q3 plus Q4 altogether. Okay, another thing to look at for a simple circuit like this, sometimes we'll show a circuit where what we say or what we mean is a resistive component, an inductive component, but sometimes we'll just write in what the power is in each one of those blocks. Okay, I notice that I'm looking at the units and I see that 75 units of watts, so that's real power. That's a resistor. Now I look at the reactive part and I notice the units of VARs, so I know it's a reactive component and it's positive. So therefore I know, oops, I was about ready to write the wrong thing, it's an inductor. I know that because it's a positive reactive power. And below here is shown just how I'm going to go ahead and calculate those based on the circuit to the left. All right, let's do a problem. I have here a circuit with 3 elements, and I'm going to label them Z1, label this one Z2, and this one Z3. Okay. And I want to find the real and reactive power of each component and determine the apparent power delivered by the source. Okay. So I want to find, basically, the way I would solve this problem is I want to find the complex power delivered to each one of those impedances, and then I also want to collectively find what the total complex power is delivered to that system. Okay, so there's my circuit. I'm going to define what Z1, Z2, and Z3 are. We'll say that Z1 is equal to 0 minus J30 ohms because it's purely capacitive. Z2 is equal to 0 plus J15 ohms because it's purely inductive, and Z3 is equal to 60 plus J0 because that's purely resistive. Also, E is defined as, again, it's a vector, and E is defined as 120 volts with an angle of 0. Okay. To find the current, I'm going to find the total current first. And in order to do that, I'm going to find the total impedance as Z1 plus the parallel combination. Oh, I almost did that wrong. It's Z1 in parallel with the combination, the series combination of Z2 plus Z3. Okay, if I do that, I'll determine that my impedance total is equal to 30 with an angle of minus 61.9 degrees, and that's units of ohms. It looks like together, because it's a negative number there, that the total impedance is capacitive. Okay, the next thing I'm going to do is find I total. I total is equal to E divided by the total impedance, which is equal to 120 with an angle of 0 degrees divided by 30 with an angle of minus 61.9 degrees, which is equal to 4 with an angle of 61.9 degrees. And the units are amps. All right. Note that the magnitude of the total current is equal to 4 amps. And we might use that later. All right. Now, I'll also find I1 if I need it. I1 is the impedance or the current through the path of the Z1, and I'll call I2 the current through the path with the Z2 and Z3 impedances. So I1 by current divider rule is equal to Z total divided by Z1 times I total, which is equal to 4 with an angle of 90 degrees amps. I2 is equal to the total impedance. This is, again, current divider rule divided by Z2 times IT, which is equal to 1.94 with an angle of minus 14 degrees amps. And if you want to, you can verify that I1 plus I2 is equal to I total. and it indeed is true. All right, now what I want to do is find the real and reactive power of each component. So instead of trying to find just one specific value or the other, I advise to just solve for the entire complex power for each one of those elements. And that way I can get any and all information that I want. The reactive power, the real power, power factor angle, complex power, apparent power, everything is right there. So this is what I advise. Let's find S1 first. S1 is equal to the magnitude of the current, I1 squared, times Z1, which is equal to 4 squared times 0 minus J30, which is equal to 0 minus J480, which is also equal to, in the polar coordinates, 480 with an angle of minus 90 degrees voltamps. Okay, this here, we'll call this P1 right here. This is Q1 right here. This is the magnitude of the complex power, that's called apparent power, and that's right here. And this is my power factor angle for that one power, that one complex power right here. That's all the information that I need. S2 is also equal to its current, I2, magnitude squared times Z2, which is equal to 1.94 squared times 0 plus J15, which is equal to, again, it's purely inductive, so it has zero power, real power, plus J 56.5, which is equal to 56.5 with an angle of 90 degrees, and the units are voltamps. Again, this one would be, I'll write it in a different color so we can see it. This is P1, or I'm sorry, this is P2, this is Q2, this is the magnitude of the complex power S2, which is called apparent power for 2, and this is the power factor angle for that impedance. All right, there's 3, now let's go on to 3 then. S3 is equal to, also equal to the current I2 magnitude squared times Z3, which is equal to 1.94 squared times 60 plus J0. This is purely resistive, so I would imagine that I'll have just a real part and no imaginary part. So that's 225.9 plus J0, which it is, which is equal to 225.9 with an angle of 0 degrees voltamps. Okay, what does that mean? Well, here is P3. Here is Q3. Here is theta VI3. And, oops, there is my apparent power, that's wrong. This is the magnitude of the complex power, the apparent power, and this is theta VI3. Now, notice that when I add those up, I'll get the total complex power, and I'll get, for the total complex power, 225.9 minus J 423.5, which is equal to 480 with an angle of minus 61.9 degrees voltamps. Okay, this is equal to S1 plus S2 plus S3. And that is equal to that. And all I'm doing is just adding the columns of power, reactive power. And that's the values that I get. So this will be this will be the total power, P sub T. This is PT right here, the total power, real power in watts. This is the total reactive power in VARs. This is my total apparent power right here, and this is my power factor angle as seen from the source. Okay. Also note that ST is also equal to the total voltage, the input voltage, times the total current, IT complex conjugate, which is equal to 120 with an angle of 0 times 4 with an angle of minus 61.9 degrees. When I do the math, I'll see that that's what this value is, and you can do that on your own. But there's the value for the real and reactive power for each component, and the apparent power delivered by the source, which is shown right here. That's 480. Okay, let's do one more problem. I'm going to skip down to the example number 3 in my notes, in your notes. And I have a system of impedances, and I have current voltage, so a circuit, and so therefore I have complex power. And this problem just shows up as a complex power problem where the total real power is here, PT is equal to that, and QT is my total reactive power, which is equal to minus 1.1 kilovars. And what I want to find is the unknown real power P2, because I'm given power here, but I don't know what P2 is. And so forth with, I also want to find the Q total, or the unknown Q, which is 3, given the other 2 and the total. And I want to draw the power triangle, and I want to determine whether or not this load right here is either inductive or capacitive. All right, so let's just redraw it. I want to give myself a little bit more space, and I wrote it down beforehand so that we can save some time and really get to the point. Okay, and that is this. If you recall, this is my total power here, total real power in watts. The second value is QT, which is my total reactive power in var, or actually in kilovars, and the top one is kilowatts. Okay, so if I were to draw or write in my equation here for total power in this circuit is equal to the sum of all the individual complex powers or elements in that circuit. So that's my equation. PT is equal to P1 plus P2 plus P3, and I just need to find what P2 is, so I just rewrite the equation to find that, and I can see that by the values that are given, my answer is 1400 watts. Likewise, I'm going to do the same thing for QT. I have the total, and I want to find Q3. So I know what QT is, I know what Q1 and Q2 is. So I'll find what Q3 is by just algebra and determine that Q3 is equal to minus 500 vars. Now what does that mean? Well, a minus 500 vars, a negative Q, would yield a power triangle shown here that's negative. It has a negative angle, and the Q is less than 0. And therefore, by definition, the impedance is capacitive, or that load is capacitive. Notice also that I have the P total and Q total as shown from the diagram as 2900 watts and minus 1100. That was just given in the problem. And so to find the magnitude of the hypotenuse of my triangle, which is what we call apparent power, call that apparent power, that's simply equal to the square root of the sum of P squared plus Q squared. And that's my triangle. So again, if I have mastered my calculator for complex numbers, I can shift between polar coordinates and rectangular coordinates and back again. And now it becomes very useful to solving these problems of complex power, because all those values in the rectangular coordinate system and the polar coordinate system have meaning. Real power, reactive power, apparent power, power factor angle. All those can be found by just using the equation to multiply a complex phasor voltage and a complex phasor current together, and I get the complex value. I get all the information that I need in one calculation. One other thing to note, is that theta VI is the angle. That's my power factor angle, and that's found by taking the inverse tangent of y over x, which y is minus 1100 divided by 2900, which gives me my angle. And again, we just discussed that because my Q is less than 0, the element in load 3 is capacitive. All right, that ought to give you enough to go on for working these problems.